is the stable temperature that we have enjoyed. That temperature is an average of land and water is about 15.5 degrees centigrade. That's the ideal temperature for land. Now, this plot which you see on the x-axis is the time from 0 to 100,000 years behind. And you will see this is with an isotope of oxygen and the concentration which mimics the temperature. On the x-axis, and you will see that oxygen over a long and the concentration which mimics the temperature. On the x-axis, stable temperature regime. It's been fluctuating. You have ice ages, it's going up and down. In the last 3,000 to 5,000 years, which is circled over there, we have had a relatively stable temperature epoch. Is an average of geologists call the Holocene. And this is the epoch in which life as we know it today has developed, has evolved. We've had this stable temperature regime. Today what has happened is this stable equilibrium in temperature is now being challenged by human activity. And that is why geologists, the term has been coined. You know this term? It's called the Anthropocene. Anthropocene, global change caused by human activity. Okay? And so basically we'll see evidence of that. You may have seen that evidence. So we'll look at one of the things. See, in the atmosphere, which are the main gases? You know this term? Nitrogen, oxygen. Carbon dioxide is a relatively smaller concentration. But carbon dioxide is important because of its characteristic of radiative forcing. Right? Like you look at a greenhouse, you have a greenhouse, the incoming solar radiation comes, but when it's being re-radiated, it gets trapped, so the temperatures are a little higher. So based on that, that is what causes that equilibrium. And the first mention of the problem of fossil fuels and CO2 was actually done by Irenaeus. You must be, those of you who are in electrochemistry and others, of course, all of us know who Irenaeus was. He had a paper, late 1800s, which talked about this. But in modern, the CO2 problem was actually recognized by scientists in the 1950s. And since 1970s, we had the Intergovernmental Panel on Climate Change. So we have not been tracking the CO2 levels in the atmosphere, but nature has provided us a record. So you have, if you just Google ice core data, and today, our students usually, rather than listening to professors, are usually Googling to find out, what he or she is saying, is it correct or not. So if you just Google it, you get a lot of ice core data. Ice core data means, if you look at the Arctic or Antarctic, your expeditions, you see there is ice, cores of ice which is formed, and as you go to the depth, as you go to a depth, you'll know that that depth corresponds to a year where it was formed. And at the time when the ice was formed, you have a frozen record of the air bubble, which has the concentration. And that's how we get this. So this is, you can see over here the ice cores, how it is. And with that, what you see is from the ice core, the y-axis is the parts per million by volume, and the x-axis is the time. You can see that for the first, from 1000 to about 1700, 1800, it's a process under control. Right? We are talking of 280 parts per million by volume, plus minus 5, natural equilibrium. After that, the second part of the curve is completely different. It is like that exponential growth curve. What happens there? What's that dividing line? What happens there? You see the year and you can guess industrial revolution. James Watt steam engine, the idea that we will actually be able to mine materials and make industrial products, industry as we know it started. And we started using coal, then we started using oil, natural gas, and that is where this is going to an exponential. So this coupled with the fact that CO2 and the equilibrium, the link with temperature, if you go to IPCC, you can see the evidence for yourself. In all of this, wherever now today you get various things, please assess and analyze for yourself. Don't believe anything which is just written. And that is the scientific way to do it. You can check that. So there is this link. So this was from ISCO data. This is now, the next one is the atmospheric data from the Mauna Loa Observatory. And you can see that that it is growing, and now we are talking of 400 plus ppm, and so it's 440 ppm. So basically the idea is, and a lot of this is due to the energy sector, due to the fossil fuels. The idea is that we have to change the energy systems, and we have to limit the CO2. We have to go towards, now all countries have now, in Paris there was an agreement to limit the CO2. Each country made a voluntary commitment. India also made a commitment, and we said we will go to reduce our emission intensity, increase fossil fuels. In Glasgow, we made another commitment that by 2070 we will go to net zero carbon. So all of this means complete change in way we operate our energy systems and our industrial systems. So this is, for all of us, it's a challenge as well as an opportunity. When we look at, now many of you may be looking at a new technology, you developed a technology, you want to analyze that technology. Typically what we do in all of this is we usually do a cost analysis. So we look at capital cost, operating cost, the annualized life cycle cost, compare it with a baseline. But in addition to this, we may also want to look at what is in the life cycle of that product. First, you look at batteries, right? You look at the production of the battery, you look at the consumption, you look at the end of the life. What kind of overall life cycle we do, what kind of, how much energy we are generating, how much energy, what are the emissions, the local emissions, the global emissions, the carbon footprint, and increasingly, emissions may not come into your cost metrics because we do not have a way of putting it into the market. But now you will have a limitation saying that you'll have a norm, you'll have an emission regulation, and increasingly you may also have, let's say, a carbon price. So it can be even a differentiator for you in terms of products. So that's another thing which you may want to look at. Overall, if you're looking at large technologies, you have a large waste recovery technology. You want to also see what happens, what's the impact, how much land does it take, what's the impact in terms of water, and what is the kind of material that you're using, is it available? And then finally also, what is the socio-economic impact, and what's the impact on equity? And these are all tricky issues. So sustainability is a multi-attribute. And specifically, if you are looking at something which is going to have a widespread impact. So I'm going to, and when we talk about a life cycle analysis, you can look at the standard ways in which you can do an LCA. We need to define the system boundaries, and we need to look at the production, the use, as well as the end of life, and then look at the entire. Every industrial process that you have essentially takes a desired set of raw materials and takes an input raw materials and converts it into, so you look at your cell phone, you have different types of materials which are there, you have a choice of that, you're using resources to do that, you create waste. And the idea is, can you change this process so that it's mostly using all the internal things, creates less waste, takes less inputs, and there are methods by which you can do that. You can look at, those of you can look at thermodynamics, and when you look at all industrial processes, actually from a second law of thermodynamics viewpoint, they're not very efficient. We're only talking of an exergy second law efficiency of about 30%. So there is possibility of changing your process completely. Will that get done? May not, because that means a lot of investments and other things. But there's often the belief that everything that has to be invented or discovered has been done, or everything is known. Now it's not. We can just sit back and let our AI bots do all the work for us. Fact is that is not true. There are lots of gaps of knowledge. We still do not understand why, when extreme events are happening. We still do not understand the dynamics of things. We still do not understand many natural phenomena, and it is important for us to keep that scientific curiosity there, as well as look at the reality and the impact. So I think that's okay. So just to give you an idea, the zinc production, which needs very high temperatures, right? It's possible to configure solar thermal beam down processes to actually do zinc production. And there are prototypes. Now in these, we have actually looked at cost, emissions, and the whole idea of the trade-off between, you can make it zero carbon, but it will be higher cost. And so these are some of the things which you may, as you do your prototype, also look at ways in which you can calculate. So now, I'll quickly run you through some glimpses of environmental research at IIT Delhi. These are all from different colleagues in different departments. Just to give you a flavor, so we've been doing some mapping of air pollution exposure as well as the health impacts, and done that with a PM at 1 kilometer spatial and temporal scales. Also looking at the burden of air pollution into different kinds of women anemia and child health diseases. The link between air pollution and climate and energy, where because of air pollutants, the impact on the output of solar, and that's also being quantified. The clean air action plans from different kinds of, again, with the pollution control boards, air pollution, climate change and health, again, some forecasting, a large number of different sensors, and I'm sure a whole host of, we have the networks, and we have, even then there are significant uncertainties in many of these studies. We've identified the relative reduction in the annual output in different kinds of solar energy resources. And we've also identified ways in which wind and solar can meet the needs, and then what happens in different months. And link between climate change and fire. These kind of fire hazards in forests, landslides, and all of this, again, using models and then projecting with satellite data. We have a whole set of researchers in our civil engineering department who work on various aspects of water. We've developed a model and a GIS-based model to look at the water security of the National Capital Region, and this is along with the Delhi Jal Board. We have created this. We've created a network to try and get real-time data of flooding and water security of NCP, and this is with the judge. There's an app where citizens can actually provide information, and all of this information can be used to track, and all the agencies, the police and the fire and the other the disaster management, they can be given this. We are also looking at hydroclimatic extremes, land data assimilation systems, simulating rivers and floodplains in South Asia, Again, these are just quick glimpses. A number of colleagues in the Department of Biotechnology and Biochemical Engineering work on various aspects of waste treatment and including looking at contaminant surveillance, treatment, mitigating antibiotic resistance in the environment, and this is including the surveillance systems to monitor pollutants, technologies for treatment, and recovery of resources. I'm not going to give you the list of all of this, but basically we're looking at anaerobic reactors to treat organics, and then some of these pilots have been done, some of them have been demonstrated and licensed. Treatment, sewage treatment for healthy reuse. Again, here also a number of pilot facilities, including a pilot plant test bed of 10 kiloliters per day, and centralized and decentralized systems at various scales. These are some of the images of that, and these are some of the anaerobic reactors, modified treatment filters, just some glimpses of some of the things which have actually so it's not just at a lab scale, it's at a reasonable pilot scale, and some of them have been used. Translational scale, 2.4 KLD pilot scale, 24 KLD STP, and energy recovery from wastewater with a pilot scale, which is treating a dairy effluents. Anaerobic membrane bioreactors, some work, this is where a very small scale, still looking at microbial fuel cells for wastewater, and this is the way in which it sort of goes, and we can get hydrogen gas. It's a small, very small scale now, but there's another project which we are quite happy with is the development of limestone calcite cement, and this LC3 has about 40% less CO2 emissions, and we are actually in this limestone calcine cement, the composition is different, but the properties are better and equivalent, and this is a multi-country study. We've had lab work, we've had field studies. There have been 25 countries where this has been tried in cement kilns, and we are actually now going to construct one of our buildings completely with limestone calcine cement. And of course, some of our researchers also embrace social media, so there's a YouTube channel which talks about LC3, DRC Asia. We've had a center in Africa, which is actively working in many African regions to popularize this LC3. We have a Center for Rural Development and Technology, and I know that some of our colleagues have collaborated with NEERI, and a number of things in that space, including efficient cook stoves, testing, standardization, looking at emissions and efficiency, test kit for remote rapid test kit for monitoring environmental contaminants. We have a compressed biogas facility and plant, and this has also been licensed. We actually run a couple of vehicles in our campus on this CBD. Some work on algal technologies and CO2 sequestration, and some work in the area of membrane-based waste treatment technologies. So I'm just going to, what I've done is I talked to you a little bit about sustainability, the challenge of the Anthropocene, and how we need to look at technologies and systems which are more sustainable going forward, moving towards net zero. We need to articulate what kind of environmental technologies roadmaps should we be working on. So you may work on your own field, but overall as NEERI, you can brainstorm and see, okay, what are we working on, what kind of roadmaps are needed. Technology development should be coupled also with systems analysis and modeling. And this is important. Different people may do it, but you may want to combine this capability because then you can actually reduce the cost of development. We also need to assess the impacts and at what level. When we do it at pilot scale, when we are going to actually scale up, what will happen? Identify system boundaries, look at entire life cycle, and these are certain tools and techniques that you may need to pick up as researchers in order to enhance your impact. Innovation is key, and sometimes when we work in a particular way, we don't often see innovation. And young people always, and you'll see school kids, you'll see college kids, they tell you, why don't we do it this way? And you say, no, 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 this can't be done. But often it's these ideas which look at things that can't be done and done. And this is something which we need to embrace, we need to encourage. And as part of innovation, collaboration may also give you different perspectives. So in doing things, you'll have a publication, you'll have a patent, maybe you'll have a prototype. But then taking that prototype to market is a different game completely. So commercialization, licensing, widespread deployment, we have to, unfortunately, in our Indian ecosystem, this is something where there are still gaps. I mean, we do talk about it, there are mechanisms, but still we need to do much, much more. Another thing which we need to understand is what is going to be the role of artificial intelligence, machine learning, data analytics. And these are things which we can embrace and use we should use our own thoughts and then look at these tools and techniques so that the routine components of it can be done. In order to be effective, we will need to be multidisciplinary, move out of our comfort zones and our silos, and look at the interlinkages between variety of things. In all of this, it's important for us, when you look at CSIR, think of who are our stakeholders. Is it industry? Is it society? Is it government? How do we get inputs from stakeholders? How do we assess and review how we are doing and what we should be doing differently? How do we take that feedback? In order to stay relevant in the changing times, it is important for us to have leadership of thought. In environmental engineering and research, NEERI should identify this is what India should do, and this is what we will do as a part of it, and this is what others should do. And this kind of vision is not left to policymakers, is not left to politicians, this is left to academics. It is up to you to define that broader vision. Please, with the domain, with the knowledge that you have, brainstorm, think, and see how we can do that. So with this, I will end. Thank you so much for listening to me, and it was really a pleasure for me to be here. Thank you.
Thank you so much, sir, for your enlightening address and invaluable insights. Your experience and vision will undoubtedly inspire all of us. We continue our work in environmental science as well. I request our director, sir, to present a memento to our esteemed guests for being part of our celebration today. Thank you so much, sir. Now it's the time to honor the dedicated service and contributions of some of our esteemed colleagues who are present today. So first we'll start recognizing the retired employees of CSIR-NEERI during September 23rd to August 24, who have given years of their lives to advancing our organization's mission. Their unwavering dedication and tireless efforts have played a crucial role in the growth and success of CSIR-NEERI. Each one of them has left a lasting legacy, and we are deeply grateful for their service. I request the dignitaries on the dais to kindly felicitate our guests today. So first, we'll start felicitating our employees who retired. So we'll start with the very special Dr. Sadhna Railu, ex-chief scientist and head. Okay, we'll move on to next. Shri Dheeraj Nitwanare, ex-technician. Okay, we'll move to next. Shri Anil Govind, ex-senior technician. Dr. Rita Rodapkar, ex-principal technical officer. Okay, Shri Anil Govind, ex-senior technician. Shri Prabhakar Ninave, ex-work assistant. Dr. M. Suresh Kumar, ex-chief scientist. Sri Sunil Kunjalkar, ex-security guard.
Ladies of here.
Shri Dayanand Nayak, ex-works assistant. Dr. Abha Sargaonkar, ex-chief scientist. Thank you all our retired employees for their immense contributions. We wish them a peaceful and fulfilling retirement filled with joy and good health. Next, we will be moving to honor those employees who have served 25 years at CSIR-NEERI. These individuals have shown unparalleled commitment and loyalty, and their long-standing dedication has helped shaping our institute into a premier organization it is today. Their consistent performance and hard work over the past 2.5 decades are truly commendable. So to start with, Shri D. Praveen Kumar, Senior Technician, Hyderabad Zonal Center. Mrs. Bhavna Sharma, Senior Technician, Delhi Zonal Center. Okay, fine. Anju Balavan. Sri Sanjay Kumar, Senior Technician, Delhi Zonal Lab. Mrs. Anju Bala, Assistant Section Officer. Sri Satish Jadhav, Senior Technician, Mumbai Zonal Lab. Mrs. Meenakshi Meshran, Assistant Section Officer, Bill Section. Sri Shailesh Kumar, Administrative Officer. Sri Rajiv Kumar Verma, Administrative Officer. His son is there. Sri S.S. Vagmari, Senior Principal Scientist. Sri S.S. Bags, Work Assistant, Engineering Service Unit. With this, we have ended over here. Congratulations to each of our honorees. But she's not
someone is ready to receive on behalf of.
Okay. I request anybody who can receive on behalf of Rita ma'am. Rita ma'am.
Actually, out of station है। मुझे एक साथ बात लेने ही आना है को आएगा।
Thank you so much. So following this, we would like to celebrate the young bright minds who have participated in the micro research project competition organized by the Jigyasa CSIR-NEERI. These students have showcased exceptional creativity, innovation, and scientific curiosity. Their models reflect the future of science and environmental sustainability, and we are truly proud to honor them today. So we have two categories. We'll start with 5th to 7th standard. The first prize goes to Swatantra Veer Savarkar Vidya Bhavan, Mahal, Nagpur. The model was on plastic recycling unit. moving on to second prize, we have Lalita Public School, Bardhaman Nagar, Nagpur. And the model was fire alarming and firefighting for forest fire using garbage electricity. Third prize goes to the Blind Relief Association, Nagpur's Mundale English Medium School. Their model was on smart dustbin. Yeah, Swatantraveer, first prize. And the model was plastic recycling plant. First consolation prize, Anjuman English Primary School, Southern Nagpur. The model was on rainwater harvesting. First consolation prize, Anjuman English Primary School, Southern Nagpur. The model was on rainwater harvesting. Second consolation prize, Northern Junior West Public School. First consolation prize, Anjuman English Primary School, Southern Nagpur. Water treatment plant. Moving on to our next category, 8th to 10th standard. First prize goes to Somalwar High School and Junior School, Nicholas Branch. The model was on domestic water treatment plant. Somalwar High School. The second prize goes to Lalita Public School. And the model was on plastic hostel concrete initiative. Third prize goes to Karmanya School of Excellence, Butibori, Nagpur. Okay. So moving on to the first consolation prize, Kendriya Vidyalaya, Ordnance Factory, Ambazari. And the model was Save Environment with Sustainable Development. Second consolation prize, Narayana Vidyaram, Chinchrugan.
This is the first Kendriya Vidyalaya.
Okay, Kendriya Vidyalaya, first consolation prize. Okay, can just click the photo and then exchange the prizes. Kendriya Vidyalaya, first consolation prize. So the next category is 11th to 12th standard. First prize goes to Kendriya Vidyalaya Ordnance Factory, Ambazari. The model was on microalgae multi-utility future energy source. For microalgae multi-utility. The second prize is Sandeepni Junior College, Hazari Pahad, Nagpur. Sandeepni Junior School. The model was on smart irrigation system, precision farming. Third prize goes to PM Shri Kendriya Vidyalaya, Ajni. The model was on water management. PM Kendriya A third prize for the category 1, Blind Relief Association Nagpur's Mundle English Medium, model Smart Dustbin.
Smart dustbin. It is really smart.
Narayana Vidyalaya for second consolation prize, model Provincia. Narayana Vidyalaya. So congratulations all the students and teachers who have participated in the competition. So this competition witnessed enthusiastic participation from 102 students representing 22 schools competing across 3 distinct categories. And the event provided a platform for young minds to showcase their innovative projects in the field of environmental science and engineering. Thank you so much. Thank you to all the dignitaries. So now I would like to invite Mr. Prakash Kumhare, Senior Principal Scientist at CSIR-NEERI, to deliver the vote of thanks.
Respected dignitaries, मेरे colleagues, students, teachers, audience, media, आज का जो फंक्शन है, so message is clear that our chief guest has talked about vision of NEERI, और हमारे जो विजन भी कहा, उन्होंने सस्टेनेबिलिटी भी कहा, और हमारे डायरेक्टर साहब ने भी ऑलमोस्ट वही कहा है कि NEERI कितना सस्टेनेबल रहेगा, क्योंकि प्रोसीजर्स और जो जिसके लिए फॉर्म हुआ था, उस प्रोसीजर